Okay, so thank you for the invitation. Thank you for the introduction. I hope I will be short since this is the last lecture or seminar of the school. Okay, so let's enter in the Hadron spectroscopy world of Jefferson Lab. It doesn't. Okay, so start from the beginning. Why it's interesting to study hadron spectroscopy, why we want to study the spectrum of hadrons. There are a lot of questions that are still, basic questions that are not yet answered, as Marco presented, and many things related to the inner structure of hadrons that are not clear at all. For instance, but basic questions like, for instance, the mass of hadrons. You know that quarks, current quarks only have a mass in the range of MeV, while the proton has a mass in the range of GeV. How it gets the mass? This should be a dynamical contribution of gluons, of the gluon field, that in some way needs to be explained. How is it possible that you move from such a small mass to something that is completely different? Or what are the relevant degree of freedom? We have a good description of partons when you look at the small distances, or you have a good description in terms of baryons and mesons if you look at the interaction at the large distance. But what happens in between? How you mix these two languages? We know that partons are the relevant degree of freedom of QCD, but on the other hand, they are very difficult to and I'm just talking about the nucleon. If you think about the nuclei, this is even more complicated. How you translate the properties of partons to interaction of nuclei within nucleons within the nuclei. So this is another basic, very, very simple questions that you may want to try an explanation. Or confinement. We know that confinement is this kind of bizarre behavior that keep quarks in colorless object, but again, there is no clear, it is a phenomenological observation, but there is no a clear explanation why only a configuration like that exists. And even in a similar scale, we are surrounded by baryons mainly, so QQQ systems. We know that there are significant fraction of mesons, QQ bar. But QCD in principle does not prohibit to have other configurations that include, for instance, gluons or combination of quarks like tetraquarks, pentaquarks, etc. Why we don't see them, and why only it seems that the most part of the stable configurations are only based on Q, anti-Q, and 3 quarks. And again, this is something that we would like to understand. And obviously, a natural place where you want to look at is a spectrum. The spectrum is, in some way, the eigenstate of the energy. So the mass of a particle is, the basic property. Obviously, then you can go, as Marco was presenting in the previous seminar, you can go, to see details of the dynamics of this object moving inside the nucleon. But, step 0, even kind of static property, you collect particles together as far as you can collect quarks, and quarks obviously are ultra-relativistic particles, so it's difficult to say that they stay together, and they are also confined in such a small volume, so it's difficult to imagine in another way. But obviously, this is something that we should be able to answer if we really want to say that we understand QCD. Obviously, there are something that we know. I'm not saying that everything is in the dark. For instance, we know that lattice QCD in particular made incredible progress in the last years, and actually you get a good grasp of the spectrum of stable particles, for instance, with ab initio calculations. So that means that you have a reasonably good understanding of fundamental states like pion, kaon, and baryon too. I mean, particles with 3 quarks. So how we usually, tackle the problem? Let's start with the simplest system. There is a QQ bar. The 3 quarks is obviously a little bit more complicated. More or less the same arguments will is equivalent, but you have 3 objects, and so it's more complicated to describe. Let's start with the simplest system we can imagine is a QQ bar. We have a reference, and again, this is something that we learn and works so well that sometimes you ask yourself, how is it possible it works so well? So, such a simple hypothesis that you pick up the two quarks and anti-quark, like a quantum mechanic, state with a specific quantum number. You have spins. We know that they are fermions. You put together, so you can combine the two spins of the two quark in a total spin. You can consider some orbital momentum. You combine all of that, and you get quantum numbers like J parity and C parity of this object. And based on that, you predict. You make as in school at the third year, probably you did it this exercise. You calculate the eigenstate of the system, and you find that there is a good, very nice, let's say, description of levels of particles that you detect in real world. Together with another little assumption that is a SU3 flavor symmetry, so you know that there are some degenerate states, more or less, again, with some corrections to the real life, but more or less with these two ingredients, a simple model where you have quarks with their quantum number and SU3 symmetry. That's it. I mean, you have 90% or 95% of the spectrum. So again, it works really very, very well. Now, if you assume that this is your kind of baseline for the description of the spectrum of hadrons, then next step will be obviously that since it is a very basic assumption, a quark and anti-quark with well-defined quantum numbers, you can ask yourself how is it possible? I mean, I can define combination of these quantum numbers that are not compatible with this simple hypothesis, and this can be a very clean way to find something that doesn't match this baseline. Doesn't mean that you understand what it is, but at least you may argue or you may say that there is something that doesn't fit in this scheme. So we have a list of possible combination of quantum numbers. This is a very powerful method if you think about, in some sense, like observing signal of the dark matter, where you observe a signal and then you need to correlate to be sure that it is a dark matter signal. But it's step 0 is to observe something. After that, you can try to interpret and make a sense of it out of it. But step 0 is just to observe it. And here is, in some sense, is similar. You have a combination of quantum numbers that are allowed based on this simple, very simple principle of two quarks, two states, two fermions close together with interacting with the potential. Very simple. You make a list of a quantum number, and everything that is not compatible with these quantum numbers that you obtain with this simple hypothesis means that probably the hypothesis is wrong. You need to add up something else. And actually, it is exactly the way you can use to look for gluons within this quark and quark. Quark are bound by gluons. We know that they have a real existence. You see them for instance, in jets. It's pretty clear. Marco explained that effect of these gluons are also visible in the dynamics within the nucleon. So how is it possible that the gluons do not show up in the spectrum? That is a natural place. I mean, gluons are the binding force in some sense. How is it possible that they do not participate at all to the dynamics of this interacting object? I mean, the two quarks, or are they, in some way reabsorbed by an effective description of what we have? That is probably the idea of the valence quark. I mean, the two quarks that we are considering are already objects that are not elementary. They may have a kind of, description, the effective description of something else that probably is the gluon. So it's difficult, to find a smoking gun and experimental evidence of the existence of gluons. Other than, one possibility is exactly looking for these quantum numbers that are not compatible with the idea of having QQ bar that may adds up. And as soon as you find new states with different combination of quantum numbers, again, you can start with interpretation, model-based, that invoke, for instance, gluons that we know that should be there within the nucleon, or within the mesons to explain them. And this is, this open up the search for combination of quarks that are not really based on QQ bar or 3 quarks. You may have tetraquarks, so 4 quarks. You may have pentaquarks with 5 quarks bind together in a single system, or you may have glue ball in principle. Why gluons are not binding together and seeds producing states exactly as quarks are binding together, or even hybrids. Hybrids meson is even more complicated because you have again these 2 quark and anti-quark with explicit contribution of gluons in your system. This is, in principle, it's all clear, all simple. QCD doesn't prohibit to have such a combination. I mean, there is nothing preventing. So how can we prove it theoretically? I mean, is it a sound idea that you may have other stuff in the spectrum? Yes, I mean, lattice QCD is in some way confirming that you have a spectrum of particles, for instance, mesons, same, again, very similarly, you can derive a plot like that for baryons. So you have standard particles, standard mesons, and beside you have also combinations. I mean, when you run your simulation on the lattice, you see that some states shows up, and they have quantum numbers that are not compatible with the standard mesons. Again, showing or suggesting that gluons may contribute. And then you can do even better than that, and this is what has been done. Not only predict the existence of these new states from the lattice, but also interpret. If you project your states on operators that have a fixed quantum numbers, in some sense you can disentangle, or you can give the combination of different I mean, as it happens when you develop the wave function, as you have the leading part is 3 quarks, and then you have DC that is contributing is a little bit less, etc., etc. Here is exactly the same. You can think that you have your projection of your wave function on operators with fixed quantum numbers, and you identify in these quantum numbers the part that is standard. So you can assign, you can consider that this part as a standard QQ bar pair, and another part within the same state, or a fraction of it, usually, that can have different quantum numbers that are, for instance, with specific combination of quantum numbers that are typical of the presence of gluons with a field that is spin 1, etc., etc. I mean, it's more complicated than just fermions. So this was done, and actually what they found is exactly what you may expect, that every meson in some sense has a dominant part that is the standard one, described by the simple quark model, quark and anti-quark, binding together, but there is also some other component in the wave function that are corresponding to something extra, something more, that may be, for instance, an indication of gluons. And obviously for states that has only exotic quantum numbers, you find that the projection on these operators is maximum. I mean, you only have that part. That again makes sense. So everything seems to be consistent. These simulations were made, these calculations were made with a pion mass 700 MeV. So we probably know after the lecture you got that this is far away from the real pion mass, but if you look at the behavior of the different states, how lattice predict them as a function of the mass of the pion that you use in your calculation, obviously you have a rearrangement, the scale changes, but let's say that more or less the hierarchy remains the same, and the main feature of this clear, let's say, description of your states remain valid. So, I mean, I think that this is, a solid and robust understanding, or let's say explanation based on first principle, based on QCD, not only on a toy model like the quark model could be. So it's a good explanation that show that you are expecting to have such states where exotics or with quantum numbers that are not compatible to QQ bar. That again, I think it's more natural than the opposite. Why they should not exist in nature? There is no reason to prohibit them. And again, if we consider this calculation if we go a step further and we consider them as a good or reasonably good prediction, we also have a mass scale where to look for. And this prediction sits for the first states that are, manifestly exotic, so not compatible with the quark model. Again, based on this theory, they are assumed to come to let's say shows up due to the gluons, but can be maybe other combination. This is just the gluon part. You may have tetraquark molecules or other weird stuff that are not included in this prediction. Obviously, here is the basic things. The exotics are expected to happen with quantum numbers that are manifestly exotics, like 1 minus plus. A combination of JPC is in the range of 1.5 GeV. So it's a very, limited energy. It's more or less the energy a little bit higher than the phi meson. Phi meson is a 1 GeV. So it's not, far away. It's really in close by to regular mesons. And this gave, let's say, a support to really open up an experimental search focus on this area. Again, obviously, the meson spectroscopy was, full steam even before the photo production or JLAB, but this was mainly focused on heavy quarks. CC bar, because obviously CC bar is a much easier system to study. You have, heavy quarks, or even heavier than that. That in principle allows for an explanation that is more theoretically sound. Light quark was always a problem. But on the other hand, our world is made by light quark, not by heavy quark. CHARM is already, a little bit far in normal world. So again, can we say that we understand the QCD because we have a perfect, that is not even the case, perfect understanding of the CC bar spectrum? No, probably not. We really need to understand also the light quark sector to really affirm that we understand the interaction and the mesons. So this is the reason why Jefferson Lab is an electron machine. I already probably heard many times this picture. Is an electron machine with an electron beam, a continuous electron beam. What does it mean continuous? Means that you have a radio frequency that accelerate your electrons running at 500 gigahertz. So it means that you have each bunch separated by 2 nanoseconds. So from the experimental point of view, from your detector, you see a continuum of electrons flowing and hitting your target. And the way it works is pretty different from CERN, from LHC, where you have a few radio frequency and you have your beam running many times through the same cavities that give the energy. In this case, you have 2 linacs. So you have really the straight section where electron goes only a few times. Every time each of these section give a 2 GeV to the electron. So the electron, run in a circle, but only for 4 or 5 times, compared to the 50,000 or 100,000 times it runs in LHC ring in a collider. So this is a completely different approach. And then when your electron gets the 10 GeV, you extract it and you use it to smash a target in this area, or when it gets another extra 2 GeV boost, and then the final electron is sent to hole D. So we have here these 3 holes where they can reach up to, let's say, 10 GeV, 11 GeV, and then the hole D where these 2 extra GeV allows you to go up to 12 GeV. That is the maximum energy that the machine can deliver. The beam is polarized, and this is the base for many experiments that Marco showed in understanding the dynamics within the nucleon. That is, another part. For spectroscopy, polarization, we'll see that is important, but it's important more because it's a filter. You can select some states using polarization. It's not really meant or used to disentangle dynamical effects. So it's just a matter of reducing, if you want, the number of degree of freedom. If you block your spin, in some sense, you are only accessing a part of the entire combination of amplitudes that describe your process. And the other thing that I want to stress is that JLAB has an intensity that is unique in the world. If you look at this plot, that is the energy, and here is the luminosity that you can reach with such a machine. This is it's 3 orders of magnitude, 2 orders of magnitude larger than what SLAC did in the all time, but it's also order of magnitude bigger than the electron-ion collider will do in the future. So it's really a complementary physics. This is the intensity frontier where you have a fixed target, moderate energy, but a lot of charge, a lot of you can access cross sections that are, or effect, if you like, that are very small using this high intensity. So it's a kind of complementarity between the existing machinery. Every time that you need to have statistics, you have to invoke. And as Marco was showing, in a multidimensional analysis, and this is particularly true for spectroscopy, but it's also true now for GPD's program or all the TMD's program, etc., where you are not only limited, as it happened in the past, in a single longitudinal variable. You want to see what happens with many variables, Q-square, X-Bjorken, transverse variables, and so on and so forth. And then obviously you need to have a lot of statistics. So this is the reason why these programs fit pretty well. With spectroscopy, it is even more true, because you really, if you want to access these states, you need to measure many particles in the final states, and this is obviously the efficiency usually of a detector is reduced, goes like the product of each particle detection efficiency. So you need to have a high intensity to see something, let's say. Jefferson Lab has 2 dedicated experiment. I mean, not really dedicated, but one for sure it is, or again, in the spirit of having a 4-pi detectors that has as a leading part of its program the gluonic excitation. It's called GluEx. You can imagine why. That is based on a solenoidal field. And obviously class 12, that is the one that Marco was talking about, that is in another experimental hall, that is based on a toroidal field. So it's a completely different, and from experimental point of view, these are totally different, let's say, concept. The advantage of having a solenoidal field is that you can build your detector around an interaction point, and so it's very hermetic. You don't have dead area all around, so it's you have high efficiency of each particle produced. The drawback of that is that you have a field that is longitudinal, is along the line. So it means that when you, in particular in fixed target experiment, you have a boost, because you start with 10 GeV particles that hit a stop target, and then you produce your particles are produced with the boost that goes in the forward direction. So the momentum flow in the forward direction. But if your field goes parallel to that, means that you have a poor resolution. It doesn't work very well. Works pretty well if you have a collider where the center of mass energy is all transferred to particles that are produced mainly perpendicular, and then you get the maximum field. For fixed target is not the ideal condition for the resolution. So you lose part of the field strength, and then it means that your resolution is not very good. But you gain in hermeticity. Class 12 is exactly the opposite. You have a toroidal field. So in that case, the field goes around the scattering plane. If you think about it, you have electron hitting the target, you produce your particle, and they see a field that goes perpendicular. So particle going straight is going to be affected a lot by the field. So you have a very good resolution, in particular for particle going forward. This also is a complication from the reconstruction, because it means that the theta angle, so the way you are producing particle is not maintained in the final, in what you observe. It's going to be bent in this direction. But okay, but you can live with that in a non-uniform field. There's a toroidal field that has weird shape. So this explains some complication that compared to other experiment at LHC, that obviously are order of magnitude more complicated in terms of number of channels, etc. But for instance, for the tracking part, this is very, 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 let's say, challenging. We have two fields. One is the solenoidal field that is the central part just meant to get rid of Müller electron. When you hit an electron over a target, you produce a lot of interaction, electromagnetic interaction at low energy. So you have a lot of low energy electrons that are you don't care, you don't want. And so having a strong magnetic field, they exit, you know, with a significant significant transverse momentum, and obviously they can in a strong field of few Tesla, they can be just, you know, sweep out. This is the idea of using the solenoidal part. And then hadrons that are produced in the forward direction hit this solenoidal field, this toroidal field in the front part of in the forward part of the detector, and they get bent and detected by systems of drift chambers and other, you know, tracking detectors. This is, you know, the concept. So while GlueX is very, let's say, compact, very hermetic, with the, let's say, low resolution, Class 12 is the opposite, is, let's say, very high resolution, but due to the fact that you have this toroidal magnet that needs to be produced by coils, and coils are big, and so they are covering part of the acceptance of your detector. So you reduce significantly, and also is not like having, you know, a cylinder. I build my detector with the cylindrical symmetry. Is, you know, I can control it, that works as I'm expecting. Here you have 6 sectors, each of them are almost independent detector, and so also the, let's say, the reproducibility between one sector and the other is, you know, more complicated. So these are, you know, the two complementary approach that JLAB decided to have, and I think it's worked pretty well when you look at the results. The way how we are producing mesons is through photoproduction. Traditionally, spectroscopy was made mainly by pion beams, because, you know, was high energy pions are produced by the primary interaction, and then you can use these pions, 100 GeV pions, or they are studied in proton-proton collision, in hadronic collision, because you produce a lot of particles, and then obviously you may have a chance to produce also mesons, and then you can study the decay. We are in a region, in an area I will show later, where we are not only interested to the decay, where you can learn from you know, how these mesons decay, but you can also look at the mechanism that produce these mesons, and this gives another insight in the microscopic structure of mesons. So the energy is not too high, is in the range of 10 GeV, and having photons has the big advantage that the photons bring spin. So again, as I mentioned before, you can use the polarization. In particular, these photons can be polarized. I mean, we can run experiment with polarized photons, and then you can use this spin in order to reduce the complexity of your production mechanism, because you select only some of them if you fix the spin. From the point of view of the cross-section, let's say, of the production mechanism, obviously these are based on theoretical calculation, because nobody, you know, measures so far an hybrid mesons, or, you know, there are hints that they exist but not yet fully confirmed, and so we can only, let's say, base our assumption on theoretical models. And theoretical models shows that, you know, since the ingredients that produce nothing special from the point of view of production of these exotic mesons, so they should be produced maybe not at the same level of the standard mesons, but not, let's say, the cross-section is not suppressed by 6 order of magnitude. Let's say that probably is 1% or so, a few percent of standard meson production. This is at least what we are expecting to have. So photo production is a good way to produce them. And I want to draw your attention here. This is quite, at least for me, was really amazing. When you compare the spectrum photo produced, that is the 3 pion. When you produce 3 pions, you put together, and this is produced at compass with 200 GeV pion beam, and this is produced in class with 5 GeV photon beam. First of all, you see that the 2 spectra are very similar. The other thing that you may want to notice is that the energy, I mean, to see, let's say, the effect of mesons in an invariant mass spectrum is usually related to some, is exactly the opposite as Marco was showing. I mean, for studying the inner part of the nucleon, you are studying smooth distribution that you interpret based on the theory. In this case, what you are really looking for is some, variation. You don't want to have something smooth because you don't, I mean, this is not the sign of a new state. A new state should shows up usually with a bump, with a peak, with something that is clearly visible. It's not completely true. I will come later on that. But you want to see some activity in the spectrum. If not, it's very difficult to disentangle what you have. So the other thing that you may want to notice is that even if you start from 5 to 200, the region where you have interaction, where you have bumps, where you have something, is very similar in the two cases. It's up to 2, 3 GeV. So namely, I mean, there is no much gain going to very high energy because the way how mesons are produced and all the dynamics, all the states are mainly limited to such low energy. Again, we are talking about light quark. Obviously, if you want to go to charmonium spectrum, you have to go to higher energy. But if you are talking about light quarks, it seems that they like to stay in systems like pions, that is 100 MeV, or in rho, that is 700 MeV, or let's say in a little bit a higher mass meson like the F2 that sits at 1200 or rho prime 1600. But more or less the spectrum is limited to 0 to 2 GeV. So this is a perfectly kinematic range that you can reach even with few GeV beam. So GlueX use how you make a photon beam, assuming that this all makes sense. So this we have good prediction that you can produce these states. The kinematic range is reasonable to produce them because this is the activity of light quark in such as limited mass range. Now, next step is you need to have a beam, a photon beam. How you produce a photon beam starting from 10 GeV electrons? There are no many ways to do it. One possibility to use Bremsstrahlung. Bremsstrahlung is a process where the electron hit a material and just irradiate gammas. I mean, the electrons are very, very interacting and they produce gammas, real gammas, and then you have a first target, you shoot your electron beam, you sweep out the remaining scattered electron, and you get the beam of real photon. Now, if you use a particular material, in particular lattice or crystals, like diamond, you may also orient your lattice of the diamond with respect to the electron beam, and then you get that the photons that you produce are polarized, are linearly polarized. And this is the way how all D is producing. You have peaks, like kind of a diffractive, distribution with peaks at lower energy. So you start from 12 GeV and you have the maximum polarization at 8, 9 GeV. That is this peak here. 8, 9 GeV, where photons belonging to this peak has a polarization in the range of 40%. And so you are happy because you have enough energy to produce these states to cover up to, let's say, 2.5 GeV in invariant mass of the particles, and you have polarization. So this is the one possibility. And also the intensity of these beams are limited by the technique that require to measure in coincidence one photon, because you have to separate part. You have the first step where electron hit your target and produce a gamma. So detecting the electron, the scattered electron, you know that there was a gamma, and you know which energy had this gamma. And then you let this gamma interact within the target. So you have to have a coincidence between what is called the tagger, that tells you which gamma you have, so tag the gamma, and the detector. This requires a time coincidence because I want to know that this specific gamma that I produce here is interacting in the target. So I need to make a time coincidence to be sure that I'm correlating correctly the two things. And when you do it, if you think about the time coincidence that you can use should be not larger, I mean, not smaller than few nanoseconds, because this is the technology we are using. So few nanoseconds correspond equivalently to 100 megahertz. So the point is that you cannot easily do beams with this technique with an intensity higher than 10 to the 8. Because it's intrinsical. At some point, you don't know who is what. I mean, you can measure gammas, but you don't know if this gamma or the other gamma that enters in your narrow time window is the one that is interacting there, while you want obviously to know it, okay? So this, but still you have beams in the range of 10 to the 8 photon per second. That is, significant high intensity that allow GluX to run and accumulate in a year time 125 inverse picobar. That is, significant statistics. The other option that you may have to produce, again, a kind of photon beam is to exploit the electron production at very small angle. So when you just hit the target, so within the target, you don't separate gamma production from interaction. You just let the electron interacting with your material, with your target, and what you do is to look at the electrons that are scattered at very small angle. Very small angle, if you think about the kinematics, means very small q square. So the electron gets deflected, and you get a virtual photon, because actually it's a virtual photon, to be honest. I mean, it's exactly like an electroscattering. The only thing is that the q square can be in the range of, let's say, 0.001. And as far as we know, at such low q square, the virtual photon behaves exactly as a real photon. I mean, there is no particular reason. There is a kind of a smooth transition between the real photon that has obviously q square equal to 0 to a low q square photons. And this is the reason why high energy beams can be, for instance, CERN Omega experiment a long time ago had beams of 80 or 100 GeV photon produced by electroproduction, exactly with this technique. And so we applied this technique. The only thing that you have to do is to measure these electrons that are scattered at small angles that usually you lose along the beam line. So you have to have a forward detector that in some way is measuring, you are sure that you are measuring your scattered electron. And so you can see that the way how, and again, since they are very close to real photons, they have the same characteristics. They can be linearly polarized. Polarization goes opposite as the energy, so higher the energy, lower is the polarization. Very similar to what happens in real photons, because again, q square is so small that the two beasts are very similar. And again, here you can reach a luminosity that are as high as very similar to the one that you have as in a real photon beam experiment. In this case, is not exactly. I mean, you cannot separate a number of virtual photon, because number of virtual photon, the cross-section interaction is also different. So you have to take into account all things, in the correct way. But at the end of the day, let's say if I renormalize my calculation to how many rho I'm producing in 1 second of the beam, let's say that the number of rho that you produce by the beam in hole D with the GluX and the electron beam in hole B with the class 12 is similar. Okay, so we have the equivalent number of Hadron production in the two ways. The advantage of using electroproduction is also that, as Marco was showing, you can also study the dynamics. So in principle, obviously, photoproduction is simpler from the point of view of the description, and is usually used to discover. I don't know states. I just shoot photons with a single variable, the energy, and that's it. And I see what happens, and I try to see if I can reconstruct my particles. In case of the electron, you have another variable that is q square. So you can change, the wavelength of your virtual photon that allows you to study how it couples to the system. And exactly as Marco was showing, also in this case, you can describe, let's say, the photocoupling is some senses, again, is a form factor, how the system reacted to photons. And it can be studied as a function of q square. And this was, for instance, used for baryon resonances to exclude the combination like the Roper, that is the first brave state of the proton, was originally people thought that was kind of gluonic excitation, so 3-quark plus a gluon. And the dynamics you are expecting, so the way how it couples to photons to let's say, virtual photons, so the behaving in Q square is very specific. That was denied by the experimental data, coming back to a more, let's say, traditional picture of the Roper in a standard way. So this was already used as, studying the dynamics. So the idea is that GlueX may discover new states, class 12 can confirm it with the real photoproduction at low Q square, and then class 12 can study the behavior at large Q square. I mean, exploring also for that specific state the behavior in Q square to give insight of the mechanism, of the production mechanism, and then confirm that there are gluons or whatever there will be inside. Okay, so this is the idea. And again, this shows a strong complementarity between the two experiments. I'm not going to go in details of the scientific program of GlueX and class 12 that include study of mesons, not only only looking for exotic, but also looking for or better studying, for instance, scalar states that are poorly known. For instance, we discover it's not really discover. We measure for the first time in class the F0980 that was never photoproduced. I mean, never observed in photoproduction, was also observed in photoproduction. Or, as I will show, that probably is the interesting things is the pentaquark. Pentaquark, we'll see how the LHCb pentaquark can be connected, can be studied in a similar way using photons with a similar reaction and check if, again, consistency. So I'm not going to go through all this detail. I just want to give you let's say a hint on how you practically you study the meson production. So there are mainly two effects. One is the decay, the other is the production. Decay means that you have particle, you detect particle in your detector. You have to be sure that the particles you are detecting in some way is kind of defining which particle, you put together the two particles and you go one step back, assuming that they decay, they are coming from a decay of a mother particle. And so you go step by step, you go back up to the original vertex that is reported in this picture here. And this is only based on distributions in space, because you have to collect this particle, define quantum numbers of these that are related to the angular distribution of particles in your detector, and then again assuming and reconstructing the quantum number of intermediate states. Go back, and then you can affirm, you understand, let's say, the decay chain. Or you can go in production. Production is a little bit more tricky because here there is a vertex. While here, it's kind of geometry. You put together, you sum up, and as far as you are able to disentangle a state from the other state, there are practical complication. But from the point of view of conceptually, it's very simple. Particle that comes from a mother particle, they should inherit in some way the spin and the quantum number of the mother particle. Its decay cannot decay as it likes. It has a quantum number fixed that determine the decay distribution. For production, is more tricky because here you have an interaction vertex that is this point here that is totally unknown. I mean, you can guess, you can have to have a model. There is no a priori, let's say, basic principle that tells you exactly how it is. I mean, we have a good understanding, but obviously it's more complicated. And again, the two information together, decay is usually used in collider or in decay like lambda B. All the LHCb program is based on decay. They are not looking at production because production is very difficult. You have to be sure that you are producing that specific particle. You need to close the kinematics, be sure that this event is exclusive. You are only producing this particle, not other stuff. Okay, to have an information on the production mechanism. So we can do that because the energy is reduced. You are not producing 1,000 particles. You are producing, 4, 5, 10 particles at most in our interactions, and then you can, handle in some way to fully reconstruct the kinematics. So all particles measured, and be sure that only and these and only these particles are produced. And as I mentioned, there are issues in reconstructing your stuff because I mean, first of all, you measure this distribution, but then you have to extract amplitudes because the definition of a resonance, the definition of is well defined only in let's say mathematical sense, and the resonance is a pole in the first Riemann sheet. So the idea is that you have amplitudes that are complex objects, and the way how interaction shows up mathematically is giving you a pole in the amplitude. This is the definition. Unfortunately, amplitude is a complex while we are measuring some real quantity, so the projection, if you like, on the real axis. So if the resonance sits, let's say the original object sits closer to the real axis, then what you are measuring is very close. The pole is mainly, you know, the peak of the Breit-Wigner. But it may happen that your resonance is produced far away from the real axis. It's hidden in the complex plane, and then the projection is barely connected to, you know, a bump or what you are expecting from a resonance. So at the end of the day, the point is that not all bumps that you see is a resonance, and not all resonance shows up as a bump. So this complicates a lot the analysis. On top of that, there is another problem that usually resonance are not sitting completely alone. You don't have one resonance and that's it. You have one resonance, then another resonance close by, and another, that they overlap because they are not, sometimes they are not very narrow states. And so at the end, you have, you know, this overlap of bumps that makes a kind of more smoother distribution. Like you can see here, for instance, the rho and the F2, you see, they are, you can imagine that the rho, that is the prominent peak, and 700 MeV is gonna go, let's say, it's producing a tail. And on top of this tail, you have the F2, that is 1270 MeV, is sitting on top of it. But you see, I mean, this case is visible for, and you may have the F0 here in between that is around 980. It is totally covered by the tail of the rho. So it's, you need to use some tricks to disentangle. And the trick, the obvious trick is that since we are looking for specific state with quantum numbers well defined, we can try to decompose the cross-section that we are measuring in partial waves. So it means that we can, each of these particles is a very well-defined state that means a very well-defined angular distribution. So what you can do is to try to disentangle. You do mainly a Fourier transformation. I mean, you decompose your cross-section just as a sum on a base. Each of these elements of the base is an angular distribution well-defined. And then what you are expecting is that at each wave, you only have particles with a certain quantum number that can contribute. So in this way, you are expecting to have the sensitivity to small signal that if you sum up all together are completely washed out by the big resonance. But if you separate by waves, in principle, you can have you know, more sensitivity to pin down a small signal. This is the idea behind the partial wave analysis. Obviously, you know, it's not so obvious because you have an experiment, so you're measuring quantity that are degraded by your detector, resolution, etc. So you have leakage of maybe if you have a signal that is 100 times bigger than another, you know, even a leakage of 1% is going to be comparable to the signal that you're looking at. So in principle, it should be nothing in this wave, but you see a leakage that, you know, give you a background that complicate the analysis. But, you know, these are practicalities. From conceptually, the point is, you know, pretty clear, pretty obvious. And for instance, we did the exercise if you run a model with different, you know, this is a spectrum of the 3 pion, the one that I showed you at the very beginning. And you can decompose in the sum of many particles that you produce that at the end of the day are decaying these 3 pions, right? The A2, the pi2, etc. And you may have a pi1, this is exotic wave, or this is obviously a simulation, so it's a Monte Carlo simulation. But it is just to give you a sense that this is, you know, the exotic wave, that is this specific wave. So my exotic particle should only shows up in this wave, and the other ones that should, in principle, they are not showing up in this wave, since they have quantum numbers that have nothing to do here. This is the total, you see 3 pion all waves when you see, let's say, the cross-section. And then here is the decomposition of in the different waves. And you see that, for instance, here is impossible to see, look at the scale. This is correctly normalized. This is a few thousand, here is 70,000. So we are injecting a fake signal in the range of 1.6 that is probably, you know, a small, a tiny one, it's a few percent sitting here that obviously you cannot observe in the total cross section. But as soon as you separate waves, this is alone in the spectrum. This is obviously, you know, unrealistic. You're going to have a contribution from many other processes that give you a baseline, give you a background, usually smooth at least, that is not, you know, picked. You're not expecting to have anything picked, but still, this shows that you have sensitivity. Even a few percent contribution can be spotted. Okay, and then, you know, we have machinery to look at the, I'm not going to go through, you know, this is too detailed. One pion, we started with a single pion production or single pseudoscalar production, going to the 2 pion, going to the 3 pions, going to the 2 kaons, and so, you know, there is a whole zoology that you can imagine. A systematic approach that, you know, every time you add a little piece to this big picture, and you understand a little bit more about your distribution. One thing that, for instance, that this is can be interesting is that partial wave analysis is the ultimate way to extract information. The problem is the partial wave analysis is complicated because the data are corrupted by the detector. So it's not so obvious. There are intrinsic and experimental ambiguities. So there may be, you know, intermediate steps like doing a moment analysis. Again, you take your cross section and you wait on spherical harmonics and you project the same, you know, similar things as again as a Fourier transformer. And then in this way, you may enhance effect like interference of different waves. And if you are sure that some particles are contributing specifically to this interference, in principle, you get access to that. And this was exactly the way how we spot the F0 980 in photo production, because it was absolutely invisible in the cross-section. We had to use this machinery to enhance the signal, like an interference, very similar how you do for a GPD program when you look at the Bethe-Heitler interfering with your process, and then you can extract your information because it got enhanced by a big signal in the interference part. Pentaquark, this was what I mentioned before. This may be, you know, relevant as a connection to Hadron physics that is running in other labs like CERN and LHCb. Spot in the lambda B decay, J psi proton K minus. If you look at the J psi proton spectrum, they found a peak, and that this should not be there. I mean, you are not expecting to see a peak in J psi proton. So we say, why? So if they spot this pentaquark, and they assume that, you know, the only way to make it if it's a genuine resonance and not some other kinematic or dynamical effect, because I mean, on top of the resonance, genuine interaction produced, I mean, states produced by strong interaction, you may also have some weird effect of the hadron dynamics that produce, you know, bump where they should not be, and this confuse even more, you know, the ideas. But assuming that the analysis was correct and you really have a peak, and the peak is a particle. Yeah, so this was mainly, you know, the analysis actually was a partial wave analysis also for LHCb, and they concluded there were not one but 2 pentaquark. So the idea is, okay, so if you can produce this pentaquark, why we can in principle do a very simple gamma to proton scattering where you produce a proton and J psi in the final state, and you are looking for a resonance in the proton J psi system. There is a very, you know, is a reversal, is the same final state, or let's say final decay state, but in a very much more controlled way. And unfortunately, what happens, I mean, we GlueX ran it, did it, measure it, and unfortunately, we didn't see anything. We were able to measure, you know, a smooth cross-section. You can see, I mean, the cross-section for this process, for J psi production, is, you know, starting from 0 and goes up. We are in a region where the pentaquark should sit, that is this line, as from the simulation you're expecting to see. If the pentaquark was there, you were expecting to see these points going up and down, showing a resonance. And unfortunately, the measurement shows, a smooth behavior. So it means it may be possible that the gamma doesn't couple to the proton to produce a pentaquark, because to decay in J psi p, you have to produce it here. So it may be possible that the way how photons couple is different, or the one that they had, they spot, the production mechanism. But this is, kind of inconsistent, because we are not expecting, we should, vertices are always the same. So if you find something in one channel, you're expecting, if your theory is correct, you're expecting, to move from one channel to another, just connecting with some pieces that you measure. It cannot be completely different. So this is, weird results that make us doubt in all this pentaquark business. I just want to conclude here about, tools. Tools are, we are using are, partial wave analysis, I already show you, but there are now a new wave, let's say, of AI in particular is bringing, a new breath in this field. And the idea is that can we use AI, first of all, to correct, to unfold the detector effect, because when you measure something, you always have two effects. One is smearing, due to the fact that your detector has a finite resolution. And the second effect is that you are not always, you are measuring the entire phase space, you are measuring a fraction of the phase space. So is AI able to support, to help? Obviously, if you, the smearing, yes, because so if you think about it, you know the transfer function of something through your giant Monte Carlo of your detector, you know how proton of 1 GeV, you have a black box here, this is a giant simulation, and you know that 1 GeV becomes a distribution centered around 1, but 1.1 and 0.9, okay? So if I know the transfer function, in principle, I can try to see, every time that I see a proton, I can go back, inverse problem. And this AI is very good to do that. So we can, we demonstrated that you can master the resolution, event by event. So in principle, you can connect each event, given let's say, the position in the detector, you go back one step and get the vertex level information. About the acceptance or the measurement in the phase space is more tricky, because we are experimentalists and we believe, since we don't know what we don't measure, you cannot invent what you don't measure. This is not fair. You cannot extrapolate. And again, AI is very good to extrapolate in the region where you are not measuring, but it's not what we want to do. If you have an error resonance that goes in your blind area of your detector and you extrapolate, you say, no, I see everything is smooth. So I'm missing a part. I say, okay, let's connect the 2 points in a smooth way. Why? Why should it be smooth? Actually, resonances are exactly the opposite. There are peaks. So you are totally not allowed. This is completely wrong. So AI cannot be used to interpolate or extrapolate between experimental data. What AI can do and can support is that you can have a better coverage of the phase space. Assuming you have a reaction, I measured this reaction at JLAB. I have the same reaction measured with the same energy at MINES, but MINES has a different acceptance. The detector is a little bit different. Okay, so it's measuring part of the phase space, but it's a different part, maybe overlapping with JLAB, but not exactly the same. What people usually do now is to take the measurement of MINES. MINES has raw data, extract a cross-section based on extrapolation on a model, and then you get a cross-section for that process measured at MINES. JLAB does exactly the same, and then you see the two cross-section and you combine the two cross-section, but this is wrong. And so, it's very easy that they do not match, because the extrapolation, the region you are inventing in some way based on a model are different. The models are different, so it's not surprise if they do not match. So the only possibility is to take raw data, combine raw data from MINES and raw data from JLAB, and then try to cover as much as you can the phase space and try to reduce as much as you can the extrapolation based on a model in the unknown measurement. And this is I mean, in principle, very easy to do, but in practice, very complicated to do. I mean, usually this is not the procedure. You extract a cross-section, you extract a cross-section and combine, and let's say compare the two cross-sections, and they do not agree. And then you quote the systematics. Obviously, I mean, they do not agree. So this is the idea. AI can support in an easy way, in a simple way, this combination. And so far, you are only dealing with the detector effects. The other thing that you can do is even more, let's say, more challenging, but I think this is the real interesting part for us as a physicist, is that you can start to use the amplitudes and try to extract directly from, let's say, combining data from your Hadron spectroscopy phenomenology. You supervise on cross-section. Cross-section is a square of your amplitudes. So in this process of squaring amplitudes, obviously you are losing part of information. But this is the one that you can experimentally access. So the idea is that if you have an informed AI, physically informed means that you are injecting some first principle in the AI algorithms, in the model that you are using, that should be general enough, not model specific, but with general principle like unitarity or very basic properties of amplitudes that should be there, and you are able to inject them. In principle, you can expect to extract the amplitude directly fitting the PDF, the probability distribution that are actually the cross sections. So this is this is a brand new method that is much more powerful than the PWA way. But on the other hand, I mean, we are just at the beginning. We are starting with that. Okay, so I'm not going to go through the future of CBAF at 22 GeV, and so I can just say that Hadron spectroscopy was a powerful tool in the past to access information about the strong forces. It's still a powerful tool to go over the basic ideas we have, two quarks connected by a potential. And we have now, in the new era, a high statistic experiment that allows you to be using sophisticated tools, analysis tool. Not only, experiment that needs to progress, but you also have to have an analysis procedure that evolve. And actually, this is what's happening with AI, for instance, in order to have, new tools to give a new information from this new experiment that are, not limited by statistics as it was in the past, now are limited by our capability of interpreting what we are measuring. So thank you very much for your attention.